This is a recording of the first lecture, the first half of the section 4.2 section that's all about experiments. Um, we're going to go through the definition of an experiment. We'll look at some reasons why we do experiments. We'll talk about good experimental design. But first of all, we need to make a distinction between observational studies as compared to experiments. In an observational study, we observe individuals and measure variables of interest, but we do not attempt to influence the responses. We watch. An experiment, by contrast, imposes some treatment. Something is done to the experimental units, the subjects, and then we measure the response to that treatment. Um, when our goal is cause and effect, experiments are the only source of fully convincing data. Okay. So we say that unless you've done an experiment, and a well-designed experiment at that, um, we don't think you can establish causality. This caused that. This happened because of that. So watch out for that wording and watch and look to see whether the results are coming from an observational study and experiment. Observational studies are problematic because of two really big issues. One is that there could be lurking variables. A lurking variable is a variable that's not among the explanatory or the response variables in the study, but may influence the response variable. We say a situation is confounding when we have multiple variables that interact in such a way that we can't tease them apart. We can't tell their effects um, uh, we can't tell one effect from the other. So watch out, know that we are going to try to control for these effects by doing well-designed experiments. Let's do a quick check for understanding. Does reducing screen brightness increase the battery life on laptop computers? To find out, researchers obtained 30 new laptops of the same brand. They chose 15 computers at random and adjusted their screens to the brightest settings. The other 15 laptop screens were left at the default setting, which was moderate brightness. Researchers then measured how long each battery lasted. Was this an observational study or was it an experiment? Well, first of all, we're going to acknowledge that the brightness of the laptops were changed. We did something. Therefore, a treatment was imposed. Therefore, this is an experiment. Okay. Note that when in my answer, I said what was going on to the units, I imposed context into my answer. So make sure that you remember that that's an important attribute of a lot of the answers that we should be giving to the College Board. Questions 2 through 4 refer to the following settings. Does eating dinner with families improve students' academic performance? According to an ABC News article, teenagers who eat with their families at least 5 times a week are more likely to get better grades in school. This finding was based on a sample survey conducted by researchers at Columbia University. Was this an observational study or an experiment? Well, I see no treatment imposed. Um, the teenagers were not forced to eat with their families. So this is an this is an observational study. Okay. What were the explanatory and response variables? Well, they were believing that the explanatory variable was eating with families. And what was the response that they were thinking they were measuring? And that is better academic performance. Or I should just say academic performance. Because if they didn't eat with the families, I think they measured worse academic performance. All right. Explain clearly why a study cannot establish a cause and effect relationship. Suggests a lurking variable that may be confounding with whether families eat together or not. Well, let me lay out this scenario. First of all, we're going to state clearly, because this is an observational study, cause and effect cannot be established. Okay, first and foremost. Now let's talk about why that is in this particular instance. Okay, let's think about the kind of kids that might be eating dinner with their families. Okay. Um, a lurking variable, for example, may exist. A lurking variable, such as family wealth. May explain the difference. Okay. Now, what do I mean by that? Um, Families with more wealth may not need to have the teenagers working. Making them more available for eating with the family. And because they're not working, and giving them more time to study. So family wealth may explain why they're eating more with the family, and it may explain their better academic performance. The observational study doesn't control for that, so we don't know whether there's a cause-effect relationship. Could eating with the family help? Could, but we don't know based on this study. Now, let's get into some of the vocabulary associated with designing good experiments. An experiment, as we said, has to involve a treatment, okay? And that treatment is applied to people or animals or subject or objects. We call them experimental units. By the way, if the experimental unit happens to be a human, we call them subjects. And we go and we try to observe a response. Um, uh, the explanatory variables may be called factors. For example, if I force a kid to eat dinner with their family, um, some of the people in the experiment may be forced not to eat with their family. Those are two different factors. Also, the factors may be set up in different levels. Some families have forced the teenagers to eat with their families twice a week, some 4 times a week, sometimes 7 days a week. That'd be different levels of the same factor. Let's take a look at an experiment that has been done. Researchers at the University of North Carolina were concerned about increasing dropout rates in the state's high school, especially for low-income students. Surveys of recent dropouts revealed that many of these students had started to lose interest during middle school. They said they saw little connection between what they were studying in school and their future plans. To change this perception, researchers developed a program called Career Start. The big idea of the program is that teachers show students how topics they learn get used in specific careers. To test the effectiveness of Career Start, researchers recruited 14 middle schools in Forsyth County to participate in the experiment. 7 of the schools chosen at random used Career Start along with the district standard curriculum. The other 7 schools just followed the standard curriculum. Researchers followed both groups of students for several years, collecting data on students' attendance, behavior, standardized test scores, level of engagement in school, and whether the students graduated from high school. Results? Students at schools that used Career Start generally had better attendance, fewer discipline problems, earned higher test scores, reported greater engagement in classes, and were more likely to graduate. Problem: identify the experimental units, explanatory response variables, and treatments in the Career Start experiment. So first of all, the experimental units in this case, um, I believe to be the middle schools, in particularly in Forsyth County. Now, you may be thinking, well, no, the experimental units are really the kids. Well, but we measured how the schools did better. Students at schools, okay? So we were really saying, did the school have better attendance? Did the school have fewer discipline problems? So I think experimental units are the schools. Um, what are the explanatory variables that we're thinking about here? I think there's only one explanatory variable, and that is the Career Start curriculum. And what are the response variables? Okay, and those are listed here. Attendance, discipline or discipline problems, uh, test scores, engagement, um, and graduation rates. Okay, what were the treatments? Well, the treatments in this case was the Career Start curriculum plus standard curriculum. There's one treatment group. The other one was just the standard curriculum alone. So we had 2 treatment groups. All right. Here we go. Here's another example. What are the effects of repeated exposure to an advertising message? The answer may depend on both the length of the ad and how often it's repeated. An experiment investigated this question using undergraduate students as subjects. All subjects viewed a 40-minute television program that included ads for a digital camera. Some subjects saw a 30-second commercial, others saw a 90-second version. The same commercial was shown either one, three, or five times during the program. After viewing, all the subjects answered questions about their recall of the ad, their attitude toward the camera, and their intention to purchase it. For this advertising study, identify the explanatory variable, and in this case, the explanatory variable was the ads themselves, and the response variable, or response variables in this case, are all these things that were mentioned. Recall of the ad, attitude toward the camera, and intention to purchase. Okay, list the treatments. Well, here are all of the treatments. All six of them are in those boxes. Did they watch it one time with a 30-second ad? Did they watch it five times with 30-second ads? By the way, the split between 30 seconds and 90 seconds, that's a level for that particular. Um, okay, by the way, ads, I should say, explanatory are the ads length and repetition. Both of those are treatments in this case. Repetition. Repetition. All right, so these are levels, and these are also considered levels. So we had two treatments, sorry, six different treatments based on two factors, and each of these factors had multiple levels. All right, moving on. How to experiment badly. So we know that experiments are the way we're going to try to get at cause and effect relationships, but not all experiments. It's not just the imposition of a treatment that makes an experiment good enough to establish causality. Let's take this example. A high school regularly offers a review course to prepare students for the SAT. This year, budget cuts will allow the school to only offer an online version of the course. Over the past year, the average SAT score of the students was 1620. The online group, they had an average score of 1780. That's roughly 10% higher of the long-term average for those who took the classroom review course. So is the online course therefore more effective? Well, the design of this experiment is simple. Okay, students had the treatment imposed upon them, and then we looked at the SAT scores. But a closer look showed that the students in the online review course were quite different from those who took the course in previous years. They had higher GPAs and they took more AP classes. So this situation is confounded. Was the increase because of the online course? Was it because they were smarter to begin with? The class interacted well with the AP situation? We don't know which thing is causing the effect. So while this is an experimental design, it's not a good experimental design because we didn't control for these lurking variables and for this confounding. So we want to design a good experiment so that we can control for confounding and lurking variables. How do we do that? Well, what we're going to need is a randomized comparative experiment. The remedy for confounding is a comparative experiment in which some units receive one treatment and similar units receive another. Most well-designed experiments compare two or more treatments. Now, comparison isn't enough. We want these two groups to be as alike as possible with the exception of the treatment, and we do that assignment by doing random assignment. Random assignment tries to use random chance to ensure that the two groups are as similar as possible. So let's talk about how we do that random assignment. Um, Definition: in an experiment, random assignment means that the experimental units are assigned to the treatments at random, that is, using some sort of chance process. So let's think of this example. Each year, the high school has enough, this year, the high school has enough budget to compare an online SAT course to the traditional classroom instruction. 50 students have agreed to participate in an experiment comparing the two instructional methods. How would you randomly assign 25 students to each of the two methods? Well, if we're told that we're going to use identical slips of paper, we could say that the names of the students are put onto 50 identical slips of paper. The slips, a period there, are put into a hat and mixed well. 25 slips are removed without looking. Those names are assigned to we'll put them in the online group. What about the others? All others are assigned to the traditional classroom, the traditional course. Okay? Important that we didn't let people choose themselves because that could introduce a confounding as well. But that's one way that we might assign the people to the two groups. But that's not the only way we could do random assignment. We could use a table of random digits. In this case, assign each student a number from, not form, from, now there's 50 of them, so we'll assign them the numbers from 0, 1 to 50. And then from the random number table, get two digits at a time. And we're going to ignore repeats and numbers not in the 0, 1 to 50 range. The first 25 students with matching numbers are assigned to the online course. All others, what are we going to do with them? Take traditional course. There we go. What about if we use technologies? Well, let's say we focus on using Desmos. So if we use Desmos, one of the commands that we can do is called the random command. We talked about that when we did sampling. And we could say randomly select 0 dot dot, sorry, parenthesis, and then square bracket, 0 dot 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 1. And then every time we use that command, it produces a number that's either 0 or 1. So this produces randomly zeros or ones. Starting at the top of the list if the random number produced is a 0, assign that person, that student, to the online group. If it's a 1, assign that student to the traditional course. Okay, now when do you stop? Stop when one of the two groups has 25 students. All other students do what? Go to the other group. And that way we get two groups of students. Okay. Now, by the way, if you think of this, 0, 1 thing, we could have done the same thing with the random number table. Okay. With the random number table, you might just do odd even and start at the top of the list and kind of have the same result. All right. So this is the kind of level of detail that we want to put whenever we're trying to describe how is it we're going to do the random assignment. So what does a random assignment, a randomized comparative assignment look like? Well, we're going to allow you to use this kind of graphic when you say I'm designing an experiment. You don't have to write it off in a paragraph form. You can say, hey, I've got my experimental units. I do random assignment to place into groups. Within each group, we get a treatment. And then when we're done, we compare the results. Okay. The control group is often getting a inactive treatment or getting a traditional treatment, where the other group is getting typically a new treatment. Think about the new treatment as being the online course and the control to be called the traditional training. Um, let's do an example. It says, a health organization wants to know if a low carb or a low fat diet is more effective for long-term weight loss. The organization decided to conduct an experiment to compare the two diet plans with a control group that has only provided a brochure about healthy eating. 90 volunteers agreed to participate in the study for 1 year. Um, Problem: outline a completely randomized experiment design for this experiment. Write a few sentences in how you would implement your design. So we have subjects. And by the way, it's traditional that we say how many are in each group. So we start off with 90 subjects. We're going to break the subjects into 3 groups. Okay. And we'll say we're going to do this using random assignment. Okay. We're going to get group 1, and that has 30 people. We're going to have group 2, and that's going to have 30 people. And then we're going to have group 3, and that's going to have 30 people. Now, what's going to happen to group 1? Well, they are assigned, they're going to get the low carb diet. It's going to get the low fat diet. And this group is going to get a brochure. And our 3 treatments. And then what we're going to do at the end, we're going to compare the results. Now, how are we going to do that assignment? Well, I think the easiest way to do assignment is I'm going to put the 90 names on identical slips of paper. Put slips in hat. Mix well. Let's draw 30 names without looking. And those go into group 1. Draw 30 more without looking. And those go into group 2. All remaining go into group 3. There we go. Good, effective random assignment. All right. When we do these experimental designs, College Board really wants to make sure that you focus on the big 3 principles of experimental design. Item number 1 is control. The control for looking variables. A comparative experiment ensures that only systematic differences between groups are the treatments administered. So the 2 groups should be as alike as they can be. And we use random chance to do that. And they get 2 different treatments, and that should be the only true difference between the 2 big groups. We use random assignment to help eliminate from possible bias that if we didn't use assignment randomly, getting roughly equivalent groups. And the third thing is replication. Let me summarize this. We need many experimental units. Okay, the more units that we have, the more likely it is that we're going to be able to see a difference if there is actually a difference between the groups. Let's take a look at a well-designed experiment. Does regularly taking aspirin help protect people against heart attacks? The Physicians' Health Study was a medical experiment that helped answer this question. In fact, the Physicians' Health Study looked at the effect of two drugs, aspirin and beta-carotene. The researchers wondered whether beta-carotene would help to prevent some forms of cancer. The subjects in the experiments were 21,996 male physicians. There were two experimental variables, each having two levels. Combinations of these levels of factors are shown in the figure below. A fourth of the subjects were assigned at random to each of the treatments. So one group took both aspirin and beta-carotene, where one group only took aspirin, but then took a placebo instead of the beta-carotene. Okay, on odd numbers days, subjects either took a tablet containing aspirin or a W pill that looked like and tasted like aspirin, but had no active ingredient, a placebo. On even number days, they took either a capsule that contained beta-carotene or a placebo. Several response variables were looked at, including heart attacks, several kinds of cancers, and other medical outcomes. After several years, 239 of the placebo group, but only 139 of the aspirin group suffered heart attacks. This difference was large enough to give evidence that taking aspirin does reduce heart attacks. It did not appear, however, that the beta-carotene had any effect in preventing cancer. Problem: explain how each of the three principles of experimental design was used in this group or in this study. Well, first of all, we'll talk about control, and that some subjects took aspirin, but others didn't. So we're able to compare and contrast those two groups. Some subjects took beta-carotene, but others didn't. There's our control. Okay, random. Which treatment group the subject belonged to was randomly assigned. Making each group roughly equivalent. And then the last one, replication. 21,996 subjects participated, making a difference easier to see if a difference existed. Okay, so there's our three major ideas of experimental design. And that finishes off this first lecture of section 4.2.